All right, in our previous lesson, we were talking about how to determine if a reaction or a process or just about anything in nature is going to take place on its own, which we call in AP chemistry, we call that thermodynamically favorable, or as your textbook says, spontaneous. Now, when we were looking at that, we were talking about something called the universal entropy. And the universal entropy, as I said before, is really difficult to work with because it's universal and you have to compute a lot of things in order to figure that out. So what scientists have done is they've figured out a way, and more particular, Gibbs is the scientist who figured this out. And actually, interesting thing about Gibbs is he was the first American scientist to actually win a Nobel Prize. So before that time, it was all British and Russian and European and Asian scientists that were winning that. So America was finally coming into strength and becoming a world power. And Gibbs was one of the first people to actually, well, the first American scientist to win a Nobel Prize. All right, anyway, so what he wins a Nobel Prize for is coming up with this concept of free energy. All right, so I'm going to try to show you the connection between free energy and universal entropy. So as I said before, we were talking about universal entropy. Remember, we're using the notation here to talk about the entropy of the universe. That is what is going to determine if a process is thermodynamically favorable. We always have to have the entropy of the universe increasing. So there has to be more disorder when we are finished with the overall universe than when we started. Now, for processes that occur at constant temperature, okay, what we're going to look at is a change in free energy. Now, free energy, I'm not going to go into the derivation of where this comes from. It's in the book. It's somewhat in my notes on where this equation derives from. I'd rather spend the time explaining how to use it rather than where it comes from. They're never going to ask you to derive it on the AP test. But essentially what it is, it's the change in enthalpy and the change in entropy at a particular temperature. And when we figure out this calculation, what we're going to get is a change in free energy. All right, so this is only going to refer to a certain set of conditions, and that's the problem with free energy, is that it's conditional. Universal entropy is that. It's universal. We can use it anywhere. Okay, so now notice what I did here is we no longer put the symbols down here. No longer am I putting down here system, surroundings, universe, because everything we are going to do from this point on will be dealing with the system. Okay, so all of this is going to deal with systems. So you would picture this as SYS. So if you don't see anything underneath these, and you most likely will not, is that we are dealing with systems. All right, so that's why the free energy is very functional for us, is that it's always going to pertain to our system, and that's what we want to have happen. We don't want to have to be bouncing back and forth between surroundings and universe and system. So from this point forward, everything will be considered system unless otherwise notated down here. That's the way they will use that same notation on the AP test. All right, so again, if you look in the notes and if you look in the book, there's an explanation of where this equation comes from. But essentially, you can connect the universal entropy change to the change in free energy change of our system. Okay, so we can make that connection using this equation, so that we find that the sign notation is what's really important here. Is that because we want this to always increase. So if we want this to always increase, we would like our free energy to always be a negative value. Okay, so we want our free energy to always be negative. So what we find here is a really, really important key concept here. Okay, and that is that when we're dealing with free energy, a process at constant temperature and pressure, which most reactions that we deal with in chemistry are. Temperature of the room doesn't change, the air pressure doesn't change much. So for us, these are really good conditions to be, to be true. A spontaneous process process is spontaneous in the direction in which free energy of the system, remember we're looking at system here, decreases. Okay, and that's the key, is that we want the free energy of the system to decrease. So what we have with that equation, we now have a way of determining whether a system or a reaction or process is spontaneous just by looking at all of the values for our system. So our change in free energy of the system is equal to the change in enthalpy of the system minus whatever particular temperature we're at and the change in entropy for our system. So everything here is pertaining to our system, and we now know how to calculate these two things. We looked at this back in Chapter 6 on the thermochemistry material. We looked at this in the previous lesson on how to calculate changes in entropy. Now we can calculate changes in free energy. So if the free energy is negative, we say it's spontaneous or thermodynamically favorable as it's written. And if it's positive, we say it's spontaneous in the opposite direction. Okay, and that means that the reaction is going to be the opposite direction. And free energy is 0, we are at equilibrium. Okay, so one last slide here, and then I'll kind of maybe make a few explanations. So here's the various ways that we can have our change in entropy and change in enthalpy. And it's very important that you're able to determine the sign notation, because you can figure out something about the reaction just by looking at the sign notation. A lot of times in the multiple choice, you don't even have to do any sort of calculating. If you just focus on the sign notation, you can predict whether something will be spontaneous or not. Let me give you an example. Let's say we go back, I think I did this example when we were talking about entropy. So let's say that we have our solid to liquid. Okay, what is going to happen to our change in enthalpy for this process? Well, we can look up the numbers and we can do the calculations. We've got the tables and charts to do that, but let's just make an approximation here. If we're going from a liquid to a solid, is this process exothermic or endothermic? Okay, it was endothermic because I have to add energy to the liquid to get it. Oh, I'm sorry, we're doing liquid to solid. We're freezing. My fault. I was thinking we were doing the gas. So this is a solid, so this is going to be an exothermic process. Energy is going to be released. So exothermic because the energy is being released from the liquid to form the solid. So we would put a negative value for our change in enthalpy. Our change in entropy, well, since we're going from a liquid to a solid, we're going from particles that are free to move around a little bit to now being locked in a rigid solid state. Our change in entropy is going to be negative as well, because we're going to have a decrease in our entropy, right? Because we're going to have less entropy afterwards. And remember, entropy is the amount of disorder or randomness in the system. Okay, so if we take a look at the chart here, if the change in entropy is negative and the change in enthalpy is negative, well, when will it become spontaneous? Well, it depends on using free energy. So delta G, free energy, is equal to this minus the change in temperature. So what I would have is if I plug in a negative here, right, and I have minus temperature minus, well, this portion here is going to be overridingly positive, right? Because a negative minus a negative makes this function positive. So right here, this portion of the reaction will be positive. The driving force here is really the enthalpy change, right? Because the enthalpy change is what's going to make this negative. For the process to be spontaneous or thermodynamically feasible or favorable, the free energy has to be negative. So let's take a look at our scenario. What happens if I lower the temperature? If I lower the temperature, liquids turn to solids. So if the temperature is going down in this process, temperature is getting lower and lower and lower, I'm going to be multiplying this by a lower and lower number. This positive becomes less and less significant, making this negative portion over here of the change in enthalpy more significant, and therefore free energy is negative. So at low temperatures, we would expect the spontaneous or thermodynamically favorable process to be the formation of a solid, which makes sense. At high temperatures, when temperature is higher, well, then this becomes more and more prevalent. So this gets multiplied by a larger number. This becomes more and more positive, which then can override the negative, right? The magnitude gets bigger, which would make this change in entropy, change in free energy positive. Notice we're doing all of this from our system's perspective, nothing about the universe or anything about the surroundings. This is positive. It is no longer spontaneous, but it would then be spontaneous or thermodynamically feasible in the other direction, which means we would melt the solid. And of course, there's a particular temperature at which this will reach equilibrium, and that temperature would be 0 Celsius or 273 Kelvin. And that would make the process equal to 0 and therefore at equilibrium. Okay? All right, so we'll look at more of this in class, and I think that's pretty much it.